So hi, my name is Dikla Oren, and I will be telling you today about sparsity-based recovery of quantum states. This work was done by myself in collaboration with Yoav Shechtman, which is now a postdoc in Stanford, and Mar Mutafi, and under the supervision of Professor Yonina Eldar and Professor Mordechai Segev from the Technion. So I'm going to talk to you today about recovery of quantum states, but let's start with some context of quantum information. Well, quantum information has been growing very fast in the past decade. It offers an exponential speedup of very difficult tasks, such as prime number factoring, which makes it very appealing. Furthermore, in the recent years, we've seen experimental realizations of more and more complex systems. These are just a couple of examples that I collected from the past 6 months. Common to all of them is the need to recover the quantum state for measurements. Now, what do I mean by that? What is a quantum state? Let's start with a simple example. Suppose you have a system with 6 channels, and you place 3 particles, one in the first channel, one in the third, and one in the fifth. Now, this state would be described by this vector. You have 1 particle in the first, 1 in the third, and 1 in the fifth channel. But another state would be, for example, having 1 particle in the second channel, 1 in the fourth, and 1 in the sixth. This is also an acceptable state. So here you can see 2 states which are described as column vectors. This is our way to write column vectors. And a state that can be written as a column vector is called a pure state. We'll come back to that later. However, every convex combination of these states, or more states, can also be a state. For example, if I take the first state with probability p and the second state with probability 1 minus p, I still get a state. This is described by this matrix. You see, we have the column vector, the row vector, and this gives us the matrix. And even more generally, a quantum state is any convex sum of such pure states. These are the probabilities for each state. Therefore, they satisfy these constraints. And the object that we get here, this matrix, is called the density matrix. This is what defines the quantum state. And when I say that I want to recover the quantum state, I mean that I want to find this matrix row. Now, under which circumstances we need to recover the state? So for example, if you have a source of photons or some other particles, you might want to know what happens at the output. You want to characterize the state at the output. Another scenario would be if you have some quantum channel where you have an input state and an output state. And if you know these two, you can probe what happens right here. And the common scenario in quantum information is where you have some state preparation. You prepare a quantum state, like the input state of an algorithm. Then you put it in the algorithm, in the quantum circuit, and you have some output state. You want to measure these two. So in all of these scenarios, knowing the quantum state is really essential. And when I say quantum state, I mean that I want to find the density matrix that I described in the previous slide. OK, so now that we've established that knowing the quantum state is essential, how do we do it? So the common approach would be to perform what we call quantum state tomography, which is a measurement scheme in which you measure the elements of the density matrix. For example, you measure this and that and that and all of the elements of the density matrix, and you have a different physical setting for each different measurement here. And the problem here is that the number of measurements required for this quantum state tomography grows exponentially with the system size. For example, if you have a state of n particles, you would need 2 to the power of 2n different measurements, each with a different physical setting, in order to recover the state. Now, this is impractical even for as low number of particles as 8. What about photon states? Now, suppose you have a state of n photons. In order to characterize this state, you would need n-fold correlation measurements. These measurements, you take your system and you place n detectors at the output. And you wait until you get simultaneous n detection events. In this case, you get one measurement here for your statistics. The problem with these is that when you go to high n, where I can be even higher than 2, you suffer from low rates which affect your SNR. This is an example from a paper where you have an experiment with 2 photon coincidences, which are these correlation measurements, and 4 photon ones. Now, these 2 measurements were taken in the same period of time, which is 600 seconds. You can maybe see it here. And you can see the huge difference in rates here and here. This, in turn, gives us practically invisible error bars in the 2 photon coincidence, but you can definitely see them here. The main point here is that as n increases, n-fold events become extremely rare. How can we overcome this problem? So our goal is to reconstruct an n-photon state from lower order correlation measurements. We will focus on a 3-photon state from 2-fold correlation measurements. Now, obviously, these measurements do not contain all the information you need to recover the state. We're using only 2-fold instead of 3-fold correlations. And the key to overcome this problem is using prior knowledge. In our case, that the state is close to a pure one. Now, I remind you, a pure state is a state that can be represented using a single vector. In the example I gave, we had 1 photon in the 1 particle in the first channel, 1 in the third, 1 in the fifth. But you can write any vector instead, just like in here. And close to a pure state means that instead of just 1 vector, we have a small number of them. This is a general representation. These are the vectors, and these are the eigenvalues. If we have a small number of non-zero eigenvalues, we say that the state is close to a pure one. Now, why are we interested in such states? So first of all, almost all the results in quantum information concern with pure states, which make them appealing to us. Furthermore, when you take a pure state and you put it in a system which evolves unitarily, it remains a pure state. But when you add certain types of noise, the common ones, what you would get is a state which is exactly close to a pure state, or perhaps can be well approximated by one. This is why we're interested in this prior knowledge. So we have a sparse state. What can we do with it? So you've heard a lot and you're familiar with compressed sensing, which is aimed at reducing the number of samples needed to represent a signal. In order for CS to work, you need 2 key ingredients. The first is obviously having sparse representation in some basis. But furthermore, you need to sample your signal correctly. You need to take measurements in a basis that somehow complements the sparsity basis. For example, if you have a signal that is sparse in the frequency domain, you would sample it in the time domain, as you've seen in earlier presentations. Now, this idea of compressed sensing has been brought to the realm of quantum measurements in these two fields. First of all, reducing the number of measurements in quantum state tomography and quantum process tomography in these 2 papers. And second of all, quantifying entanglement, which is a very important resource in quantum information. This was done right here. However, sparsity itself has opened the door for a variety of applications. You've heard about some. For example, sub-Nyquist sampling, sub-wavelength imaging, phase retrieval, ankylography, and many, many more. So we have a sparse signals. What can we do with it? Let's concentrate on the physical system. It will be obvious in a minute. We have an input state of 3 photons that we want to recover. And we inject our photons to an array of coupled waveguides. The photons propagate in the waveguide according to this equation. This is the quantum operator describing the creation of a photon in a waveguide. And this describes the propagation in the same waveguide. But because our waveguides are coupled, we also have this term here, which says that the light can also hop between waveguides. Now, why are we doing that? Why are we adding this array of coupled waveguides? So first of all, we get from it a discrete set of mode, which is very desirable in many quantum information applications. We can also solve this propagation, which is very helpful, as you will see. But the most important thing is that the coupling between the waveguides spreads the information. As I said earlier, in order for CS to work, we need a sparse representation, which we have. We have a density matrix with a small number of non-zero eigenvalues. But we also need to sample our signal correctly. This is what the coupling does. What do I mean? Suppose you have no coupling. Forget about this. So you inject a photon to the array, to some waveguide, and it propagates. That's all you get. But once you add the coupling of the waveguides, then the light can propagate to neighboring waveguides. And that's how, when you measure the output, you get information from every measurement. And this is the second key ingredient for our approach. OK, so we talked about measurements. Let's be a little more specific. We want to recover the 3 photon state. And we basically need the 3-fold correlation measurements, where you take 3 detectors and wait for 3 simultaneous detection events. However, we don't want to do that. We want to use the 2-fold correlations, and that's it. So we have a linear set of equations and a linear set of measurements, where these are the measurements. This is the signal that we want to recover, which is derived from the density matrix that I described earlier. And this matrix here that relates the signal to the measurements is derived from the propagation in the array. So we have a linear set of equations, but it's an underdetermined system because we're using only 2-fold correlations and not 3-fold ones. How can we solve it? We ask ourselves, can we exploit the sparsity in our state in order to overcome this problem? And the answer is yes. How do we do that? So we have this underdetermined set of equations, where this is the signal we want to recover. These are the measurements, and this is the matrix that relates them, once again, derived from the propagation in the array of coupled waveguides. This vector is a probability vector, but we know that it only has a small number of non-zero elements. So we basically would like to solve this problem, where we want to find P with the smallest number of non-zero elements. This is what tells us it's a sparse vector. We want it to be a probability vector. These are these constraints. And we also want it to be consistent with the measurements that we do have, the missing measurements, but we do have some. The trouble is that solving this exact problem is not possible. Instead, we can replace it. A common approach would be to replace it with the norm 1 instead of norm 0, which promotes sparsity. However, if you look carefully, you can see that every feasible solution, in our case, due to these constraints, has norm 1 of 1. Therefore, this alone would not help us. So we took a different path. And we have an iterative solution to our problem, which stems from ideas found in these 2 papers, where we have an iterative solution with 2 stages. At the first, we increase the support of our signal, and we try to solve our problem on the new support that grows. And once we can't improve this further, we keep the size of the support constant, but we try to change the support itself. And this is what brings us the following results. So I remind you the setup. We have a 3-photon state that we want to recover. We inject it to an array of coupled waveguides, and we take only 2-fold correlation measurements in a single setup. These are numerical results, where you can see an example of a recovery. Here you have an original state with 7 non-zero eigenvalues, and you can see that it is recovered very well. You can basically, you can't see the difference between the original and the recovery. And here you can see the performance of our method for different number of non-zero elements. The fidelity is just a measure for how close the 2 original states are, where 1 is very good, and as it decreases, it's not as good. So as expected, when you have more non-zero elements, it works less good because we use the sparsity in our method. Here, the recovery probability is defined as the fraction of successful reconstructions, where successful means fidelity over 0.9. So once again, as the sparsity increases, the number of non-zero elements increases, the recovery probability decreases. Here is another example in the same setup, however, now in a different basis, one including entangled states. As I said, entanglement is an extremely important resource in quantum information. You can see again that the recovery works very well, and it behaves as expected when you increase the number of non-zero elements. If I want to summarize up till now, we have exploited the sparse nature of quantum states that appears in many systems. This allows us the recovery of 3 photon states, which are sparse in a known basis, from two-fold coincidence measurements. What about a relaxed version of this prior knowledge? So far, we had this representation of the density matrix with a known basis and unknown coefficients. So we had to recover these, and we knew these. Now, we want to have an unknown basis. That is, we don't need to know this anymore. So we have a density matrix, which has a sparse representation, but we don't know in which basis. OK? Now, I want you to note that this matrix has low rank, OK? Because it has a small number of non-zero eigenvalues. One possible solution to that would be to recover a combination of the basis and the sparse signal from several signals, as done in a blind compressed sensing. But in this specific problem, we took a different path that I'll describe in a minute. So I want to remind you, we have quantum state tomography, which requires different physical settings. You need to change polarizers, and you need different and a lot of optical components in order to recover a state. But we don't want that. We want to replace it with a simple version, a simple, efficient, single setup, and we want to recover the state from measurement in this single, simple setup. However, we can't really do that because there's missing information. That's why we're adding vacuum ports. Remember those channels? We add channels in which there are no photons. We know that. It seems like it gives us nothing, but it does give us more measurements at the output. Furthermore, we change the evolution of the state. Instead of propagating in just a coupled array, we change the evolution to mix the input ports even further. And with these 3 ingredients, a density matrix, which has a sparse representation in an unknown basis, the vacuum ports, and the mixing evolution, we go to solve the following problem. So once again, we have linear measurements, but an underdetermined set of equations, since we're using only a single simple setup. We need to solve it, but this time, we don't know the basis. So we're trying to actually solve a problem in which we want to minimize the rank of the density matrix, because we have a small number of non-zero eigenvalues. This is the same as the 0 norm that we had in the previous problem. But only now we don't know the basis. So we want to minimize the rank, and we have to comply these constraints. This gives us the physical nature of our density matrix. As you remember, this stems from the probabilistic nature of the eigenvalues. And this tells us that we have to be consistent with the measurements that we do have. So in order to solve this problem, we replace the rank minimization with the log det heuristic. And then in order to actually solve this problem, we replace it with a linearization of the log det and solve it iteratively. So this comes from the linearization of the log det. And these are, once again, our constraints of probabilistic eigenvalues and consistency with the measurements. Now, with this at hand, we solve the following problem. So we have a setup, a single setup, with 3 photons at the output, and measurements, 3 photons at the input, and measurements at the output. And from this, we recover, this is an example for a recovery. This is the original density matrix, real and imaginary part, and this is the recovery. And it has great agreement. Here, more quantitatively, you see that the fidelity of the recovery is very close to 1 when the rank of the density matrix is low, as expected, because this is how close we are to a pure state. And also, the recovery probability drops as we increase the rank, once again, as expected. Now, I want to stress that without our method, it was impossible to recover the density matrix from this set of measurements, which is much simpler. So with this tool at hand, we try to solve another problem. When you measure a state of several photons, you would want to count the number of photons. You need it in order to characterize the state. But the problem is that single photon counting models are more expensive, not as efficient, and they often have very long fall times, which really limits your rate of detection. On the other hand, when you have ordinary detectors, which are more available, then every click represents more than 0 photons. But it can also be, it can be 1 or 2 or 3 or even more. You don't know. You can't tell the difference. So we want to use the simple detectors that only know how to click, not count, in order to recover the state, which you need counting detectors in order to do that. So our solution is to say, OK, we have 3 photons in the system. Why not use only coincidences where you have 3 different detection events? Now, in this case, since you have only 3 photons, you know that counting and detecting is the same, because you have 1 photon in every detector. The problem is that you are left only with a small fraction of the measurements, but we know that it's not a problem for us. So we want to recover the state with these simple detectors in a single setup. Once again, you can see an example and some performance. This is the original density matrix, real and imaginary part. This is the recovery. And also here, you can see that the fidelity is very high when the rank of the density matrix is low. Once again, this is expected. And the recovery probability also drops when you increase the rank. Once again, we couldn't have recovered the state, the density matrix, from the same set of measurements without our method. OK, so let me summarize. We showed that using sparsity, we can recover the state of 3 photons, which is sparse in a known basis, from only 2-fold coincidences. We can also recover a 3-photon state for measurements in a single setup. That was also in a single setup. But even when we don't know the basis, we can still do that in a single setup. And we can also use this scheme to recover states without number resolving detectors. Now, for our current and future work, we're working on formulating this for a state with a fixed, up to a fixed number of photons, which allows more losses brought in. We are interested in the scaling of the number of required measurements with the system size. And we want to implement this in an experiment with only clicking detectors, the simple type, and still recover the state. Thank you.